So this is fall of 18? 19? Problem number 1. Y is equal to 4x. Y is equal to x cubed. Okay, so we're going to find the area, the volume about x using washers, volume about y is equal to 10 using shells. Okay. So that's what we're doing here. So let's draw the picture. The picture will tell us how to find the area anyway. All right. Come on. No.
First quadrant.
First quadrant, because y is equal to x cubed, is that. And then y is equal to 4x is sharp. Yeah, we better do quadrant 1 because it'll intersect twice. So let's do quadrant 1 only. Y is equal to 4x will intersect up here. So you have your choice on this one. If you want to integrate top minus bottom dx or right minus left dy, it doesn't matter. You need to find where they intersect. So we set 4x equal to x cubed, which says that x cubed minus 4x is 0. Pull out an x. So they intersect 3 times. It's 0, 2, and negative 2. But we're in the first quadrant, so we can ignore that other one. So this point is x is 2, and in either equation, 2 cubed is 8, 4 times 2 is 8. So let's do area as a dx integral. Top graph minus bottom graph. So top will be the line. The line is 4x. Bottom will be x cubed, dx, and then we follow the x's on the integral sign. So we go from 0 to 2. But now, for fun, let's do right minus left dy. Who wants it?
4.
1/4 y is going to be left.
Yeah.
So what's the right graph going to be?
Cube root y.
Cube root of y. So we've got cube root of y minus y over 4 dy and 0 to 8. Okay? Okay,
When are you restricted to using one of those? Like one versus the other?
if it's not simple for some reason, right? Suppose you had, I don't know, y is equal to sine of x. And then y is equal to x. So if you did this way, you'd have to use an inverse sign, right? Or heck, couldn't even do if you didn't have that. Right? So this one's simple this way, but not simple that way because we've got 2 sides of the sine of x.
Right.
And that's not even in the, I guess you'd have to use symmetry or something. That's a bad example. It's a bad example. Yeah. Yeah, if you have a parabola this way, a line that way, right? It's horizontally simple, but it's not vertically simple. Okay, so when we're using washers, we partition perpendicular to the axis. So we'll draw this picture. It's in here and here. And our partitioning element will be perpendicular. We're going about the x-axis. So our rectangle has to be perpendicular to the x-axis. And then when you revolve that, it makes a washer. And our plan then is outer radius squared minus inner radius squared. And the rectangle going that way has a base width of dx. So in this example, it's going to be a dx as the thickness of the rectangle. So pi outer radius squared minus inner radius squared dx. So I've already got everything in terms of x. Y is x cubed, y is 4x. Which one of those two equations gives you the outer radius?
4.
The 4x is furthest away from the axis of revolution. So 4x is a capital R, and x cubed is the little r. So we have volume is equal to pi times the integral, outer radius squared minus inner radius squared, thickness is dx. And then we're going to follow the x's. X goes from 0 to 2. So let's make a big picture for number 3. The camera, I guess. It's not going to follow me. Backwards. I'm going to turn my camera here. All right, so let's make a bigger picture here so that you can see what happens when you partition this region. So y is equal to 10. That's going to be up a bit because this point was 2, 8. Y is equal to 10 is up here. We want to go around that line and we want to make a shell. So that's a horizontal line. Our partitions have to be horizontal. Okay. So shell. You know, remember the formula for the volume of a shell? What's our game plan? 2 pi r h times the thickness. That's the thickness of the rectangle that I just drew. How thick is that rectangle? Is that a dx or a dy?
dy.
That's a dy. So everything has to be in terms of dy. So let me write this equation over here is the cube root of y. And this equation over here was x over y over 4. What do those tell me about my 2 pi rh? How do I use those two equations to get something here?
So from the integral of 0 to h.
Okay. R is measured this way.
Yeah.
So it will be
Is it cube root of y minus, 10 minus the cube root of y minus y over 4?
No, don't get
You don't
that
need
mixed
the
up with the
intermediate?
h. We're going this way, so that's
Okay.
all in the y direction.
Yeah.
So it has nothing to do with the graphs.
10 minus what?
So 10 minus
Oh,
y.
okay.
10 minus y is the r. Now the height of that little pink box, which is going to be the height of our shell, is right graph minus left graph.
Oh, that's what the, okay.
So cube root of y minus y over 4. So that's r, that's h. And then dy is the thickness. Okay. show you this one. All right, let's keep with the same two graphs. Let's just change the line of revolution. Let's keep the first quadrant version of y is equal to 4x and y is equal to x cubed. And let's revolve about x is equal to 2. Let's do one of each. So let's do washers first. And then let's do shells. Take the same graph. Other way. We're going to take the same two equations. We're going to revolve out x is 2, and we're going to set up the interval with washers and then with shells. So the picture for the first one. Y is equal to x cubed, y is equal to 4x. This point was, what I said was 2, 8. X is equal to 2 puts us here, right through that point of intersection. So washers have to be partitioned perpendicular to that line. Shells have to be parallel. Washers are perpendicular. So washers are going to be this way. My yellow. I'll do the shells in yellow if I can find my yellow. This yellow's gone. There's yellow. No. There it is. So that's going to be washers. That one's going to be shells. And for washers was pi outer radius squared minus inner radius squared d whatever. The plan for shells was 2 pi r h d whatever. An air out here. Stay, I said.
So the washers will be 5 under the integral of 0 to 8. Y squared over 16.
Okay.
I got 2 minus y over 4, all that squared.
They go all the way back from here. So 2 minus y over 4 all squared. All squared. Okay,
Minus 2 minus the cube root of y.
that make sense? Okay. shells. So the H is going to be top graph minus bottom graph. What's going to change is R. When you change the axis of revolution, in every case, it's the R that changes. And that little yellow box that I drew there is a dx box. So we're going to do everything in terms of the variable x. So usually the R is just the distance to the axis. Well, usually always. Distance from that yellow box to the axis of revolution. So I need to know how long this segment is here. How long is it?
4 minus x. 2
2 minus x.
Yeah.
2 minus x. 2 minus x is going to be the R. And now you tell me how tall that box is.
4x minus x cubed.
Top graph minus bottom graph. And then this follows the x's from 0 to 2.
So if the axis was on like the negative side, like -1, how would that change the washer?
Okay, let's look at it. If we did this, and you said put this back here, x is -1. Okay, so if x is -1, then this pink box has to come around here. And so it has to go outer radius and then inner radius. It's still going to be dy. What's the outer radius going to be if we go around x is -1? About x is equal to -1, you still have a dy, so it's still everything the same. What changes here is I'm going to hit the x cubed graph, but remember dy. So it's the cube root of y plus 1.
Yeah.
That's outer radius. Now the inner radius to the yellow, to the pink, to the this end of the pink box.
1 plus y over 4.
1 plus y over 4. Y, I said. I don't know where this pi came from here. That should be a y. Y is 8. And so if we go around x is -1, what changes with the shells? Not the height of the box, right? Height of the box stays the same. Now we got to look at the distance from the middle of this yellow box to that line.
X plus 1.
X plus 1. And they follow the x's. Help the heck out of that problem. Sir,
We do an area of color graph.
area of a polar graph? What's your favorite polar graph? You don't have any?
Rose curves is
You
there.
like rose curves?
Symmetrical.
They're nice and symmetrical, okay. So how about cosine of, find the area enclosed by one petal of y is equal to the cosine of 2 theta. How many petals does r is equal to the cosine of 2 theta have?
4.
4 petal rows. And you said you like cosines because they're symmetric to x. So all you have to do is figure out, because the tip of the petal, tip of one of the petals is going to be when theta is equal to 0. Right, because cosine of 0 is 1. So now we have to figure out where it opens and closes. So what number goes under here so that I take the cosine of that angle to get 0?
0. No. Pi over 2.
Pi over 2. So for what value of theta is the stuff under my hand equal to pi over 2?
Pi over 4.
So that tells you have that. That's half of our petal. The other half is down here, of course. But if you found that and doubled it, if you integrate from 0 to pi over 4, you'll get the area of half of that petal, so double it, and you get the area of the whole petal. Do you remember the formula for the area of the polar curve? No, that's the arc length.
I really just want to say it's the integral of outer radius d theta. I mean, outer radius squared.
Right, f of theta squared d theta, but there was something out
One
here.
half.
1/2. 1/2 f of theta squared d theta. So that's what you're setting up here. So we're going to just do that shaded part, then we can get rid of that half by doubling it. And we'll go from 0 to our pi fourths. And there's our f of theta, so we got to square it. That part okay for you?
Yeah.
All right, now you got to integrate the cosine squared, but it's cosine squared of a multi-angle. So you go do a Udu substitution. You can take U to be 2 theta, so that 1/2 du is going to be the d theta. So now you're integrating cosine squared of u times du, but you've got a new 1/2 out front from the Udu substitution. What's the formula for the integral of the cosine squared of u?
Plus sine 3.
U over 2 plus
Sine 3 over
sine of 2u over 4. Now I got the 1/2 from the step above. And u was 2 theta. And we're going from 0 to pi over 4. These two's cancel. I do the trig function first because I know 4 times pi over 4 is pi, sine of pi is 0. Sine of 0 is 0, so we get no contribution from that one. Theta is going to be pi over 4 minus 0, so theta is going to be pi over 4. The area is pi over 8. Is that too fast?
Way too fast.
Okay.
Yeah.
Yes, it was too fast?
No.
Oh.
Can you explain how you get where it closes again? I mean,
I explained about where the trig function is 0. What angle makes the trig function go to 0? So what angle makes that 0? Okay, so I know one of the zeros of cosine is at pi halves. And so if I just solve this, what angle is 2 theta got to be pi halves? So solve for theta by dividing by 2.
So after we figure out where it closes, how do we figure out like how to graph it? So where pi over 4 is where it closes. So is that where
And
the
pi is
axis
where it hit its tip. And we know cosines are symmetric. So this is pi over 4, and that's negative pi over 4.
Okay.
And then we knew there's 4 petals, so they should all be 90 degrees apart. 360 divided by 4 gives us that all the petals are going to be on the axes.
Oh, okay. So there's normally 4 more petals. But we
There's a
just
total
do
of 4
one.
petals. If it's
Okay.
even, there's twice this number.
Mhm.
If it's odd, there's that number.
Where did that 2 come from? For the 2 times 1/2 on the second step? Right.
Using symmetry.
Oh,
So
okay,
instead of
gotcha.
integrating from negative pi over 4 to pi over 4, I'm getting just the top part of the leaf
Okay, thank you.
and doubling it. I usually do that for cosines because they're always got their first leaf on the x-axis. Yes, sir.
For a sine rose curve with 4 petals, would the middle of the petal be going through pi over 4?
It would, because sine is 1 at pi halves. So if 2 theta is pi halves, then theta has to be pi over 4, right? And so sine of what is 0?
0.
0 and pi. So if 2 theta is 0 and 2 theta is pi, you get the numbers that make it close. So 2 theta is 0 gives me theta 0. 2 theta is pi gives me pi over 2.
And then you
So
could
you just
use
integrate from
symmetry.
0 to pi over 2 to get the whole first petal.
And could you use symmetry again on that one too? Okay.
Good, but why? Because you got 0 and pi over 2, those are good
Oh,
petals
that's
to
okay.
use. Okay? And if it's cardioid, you don't have to worry about anything. Cardioids are centered on the polar plane, so you just integrate 0 to 2 pi. Only the rose curves, you have to figure out where they open and close. Didn't want that piece of chalk anyway.
Can we do one of the spring ones?
A spring one. See if I got a spring one anywhere. I'm going to show you this test. This test is hard. There isn't any spring problems on there. I will give you that one. That will scare you to death. Let's see, a spring one. Spring one. I guess I make up a spring one.
I have one on.
You have one. I'm ready then.
Okay. It says a spring whose length is 2 feet exerts a force of 100 pounds when stretched to a length of 2.25 feet.
Force is 100 pounds to stretch to what?
2.25.
2.25 feet.
And they want us to set up an integral to find the work done in stretching the spring 1 foot beyond the natural length. So 3 feet, I guess.
All right, so when we set this up in terms of the variable x, x is always a measure beyond natural length. So we set natural length at 0, and all the other x's go beyond natural length. So this corresponds to x is what?
2 or 0.25.
0.25, or 1/4 of your into fractions. 1 foot beyond its natural length, this corresponds to x is 1, right? Okay, so what's the general overriding principle relationship between force and the spring constant? What do we know about the force in spring?
Is it F equals KA?
F is equal to kx, so that's what we use here. We use this first information to find k. So we're going to put 100 here. I'm going to use a fraction here, because it's easier to solve, right? If I multiply both sides by 4, I get k. So k is 400 for this particular spring. And then work is an integral. Force times distance. Force is kx, distance is the dx. Right? Work is force times distance.
So we times 2 to 3.
We're going 1 foot beyond natural length. That's x is 1.
0 to 1.
This is x is 0. So we're going to go 0 to 1. And 400 times x dx. So all I got to remember is that natural length corresponds to x is 0. Right? So you can draw the picture. Do your 2 feet here. This corresponds to x is 0. And then to 2.25. That corresponds to x is 0.25. And then the x is 1.
So is this the only formula that we need to remember for springs?
Yep. It's the old hook. We only have that easy formula.
That's good.
So would the problem be, like, let's say we're stretching it from 2.25 to 3 feet?
Uh-huh.
Would it be from 0.25 to 1?
Yes. The 3 feet would be, yes, 1. Yes.
So is the format between most of the finals the same? Like I see on this one, there's one physics space. So there's probably going to be one physics space on like power.
Like pumping water or
Yeah.
force on a fluid force, or they're doing the work done in stretching the spring. That'd be my guess. Yeah, that'd be my guess.
Can we do one of the fluid force ones?
Fluid force. Okay. So fluid force is a two-dimensional quantity, right? Because force is only acting on the vertical plate, not on the horizontal. On the horizontal, it's constant. It's just, depth times area. But this way, we've got to go depth to a strip times the area of the strip. So force, fluid force, is the depth of the strip times the area of the strip. And it's a rectangular strip, so that's just how long it is times dy. And so if my plate was here, the parabola y is equal to x squared. Maybe that's the face of a dam. And maybe the dam is right here to the height of the water at y is equal to 9 somethings feet, I guess. It's a tiny dam, the little 9-foot parabola dam. And so we want to find a force acting on this face right here. So imagine that face cut up with a bunch of rectangular strips. You find the area of each rectangular strip and how deep that rectangular strip is. Set that up in an integral and you've got force, and then you've got to know the density of the fluid. Let's say that this is ordinary water, so we can use that our density of this liquid is 62.4 pounds per cubic feet. What's the units of force? Pounds. So make sure you set up an interval where your final result is going to be pounds. So that's why I say we take our density times our area. What's our unit of area?
Feet squared.
Feet squared, so that cancels 2 of those, times the depth. That's going to be feet squared times feet. So all these cancel, leaving you with pounds. Density, area of the strip, depth of the strip. And that'll give you an integral. So that's the plan. You don't see a strip, so let's put one in there. There's your depth. Density times the area of the strip times the depth of the strip. Set that up as an integral. That's a force integral. Density. All right, so the strip is a rectangle, so we just take length of that strip times the width of that strip. I've got the width of the strip and everything going in the dy direction, so we're going to do everything dy. So this portion of the strip has a length of dy. How long is that strip as a function of y,
Normally it'd be 2x, and then we can convert using.
right? L is 2x, where x squared is y. So x is the square root of y.
Which root?
So the length is 2 times the square root of y. So 2 times the square root of y times dy is the area of the strip. And now we need how deep that is. How far is that strip placed beneath the surface of the dam?
9 minus y.
9 minus y, very good. And what about the numbers on the integral sign? 0 to 9. Okay. What changes if I move that dam further, or whatever plate that is, deeper? What if I put this at 12, but the top of the dam is still at 9? What changes in the formula,
Your bounds of the integral stay the same,
right?
but your depth changes.
Just this one number right here, right? That would become a 12 minus y if I had this submerged. Everything else stays the same. So pay attention, this was in pounds per cubic feet. Area here was in square feet. Depth was in linear feet. So those two multiply together to give us the cubic feet and cancel with that cubic feet in the denominator. And now force is in pounds. So what's different between a force integral and a work integral?
Units.
The work integral, I need 3 dimensions, right? I need a tank maybe coming out of the board with the parabolic shape and a flat top. And then we have to multiply by how deep that is, because we need 3 dimensions then, right? We need the length, the width, and then how deep this is. And so if this were 20 feet, a trough has that shape and it comes 20 feet out at you, then we would just stick 20 here. Because you have a volume as opposed to area. The length, depth, and the other dimension, or not of variables.
So if it was just work, the only other variable is like how deep it
How
will be.
deep it
Can we
is.
just multiply it?
That's right. That's right. Right?
Really over the top question,
Okay.
we're going from 1D to 2D seems very linear, about 40.
Like 4D, like what are we going to put a time? That it changes with respect to time as well?
I mean, it's
dy
like
dt.
length times width, just to the volume, just multiply by the measurement.
We're getting into,
Physics.
I don't know what 4 dimensions looks like unless we have time. How does volume change over time? I know my volume has changed over time. You just want to pull up a test and do a test, or
Yeah.
still just pulling up questions at random? I don't want to do things that you already know how to do. That's my point. All right, let's continue on with the fall of 19. And problem number 2 says, find the arc length. Set up the integral that finds the arc length of y is equal to 2 times the natural log of x. From x is equal to 1 to 3. So arc length comes from the distance formula. That'll help you remember that arc length is that formula that has the square root sign in it. This is still the fall of 19 practice final. Problem number 2, fall of 19. Okay, so distance formula. Distance formula is like also the, what is that called? A vector. Magnitude. Good. Gosh, that word was gone. Woo!
I was gonna say absolute value, but that's.
Yeah.
But it is. It's absolutely. I did it twice. It's like magnitude, right? Component squared plus component squared added together. So what are we adding together in here when we find the distance? 1.
Y prime.
Uh-huh.
Squared.
So what you can think of that as 1 squared plus y prime squared, and then the dy. So it came from having a delta x squared plus a delta y squared. And remember, we divided out by the delta x squared, oops, dx. And so delta y over delta x became the y prime squared. So once you remember the formula, everything else is poof, easy points.
Oh.
Remember how to take derivative of log of x. 1 over x. So the numbers are given to you here, 1 to 3. 1 plus, here it'll be 2 over x, all squared, dx. And you're not asked to integrate, just asked to set it up.
Oh. Yay.
Okay? So it is up to you to learn the formulas again. Don't miss a problem because you forgot the formula. There aren't that many formulas in this class, just about 2 to 3 sheets full. If you say them in words, right? Areas, top graph minus bottom graph, volume is either 2 pi RH or pi outer radius squared inner radius squared. Then you don't have to memorize, you just kind of do it. Okay. Third problem. Third problem is evaluate integrals. Okay, so the first integral to evaluate is the product of the sine cubed of x with the cosine of x. That's right, that's a Cal 1 integral. Somebody puts a Cal 1 integral on your test, don't even do it. Say, I'm insulted by you give me a Cal 1
How
integral.
dare you?
I am not going to do a Cal 1 integral in my Cal 2 class. And you erase it and you make it a Cal 2 integral. You do something like this. That's a Cal 2 integral. That's a Cal 1 integral. Right? U is sine of x, d is cosine of x. So we have u cubed du. Much respect if you change a Cal 1 integral to a Cal 2 integral, though. I give away points like crazy on the final. Right, you do the fourth. So what was the difference between this one and the Cal 2 integral? So it's not much different, is it?
No,
Just
no.
one additional step. Take the cosine squared out. But instead of writing cosine squared, what do we write?
1 minus sine squared.
1 minus sine squared. And now it's another u du integral. Right? U cubed. So it's not that much harder. That's all it takes to get my respect. So you have u cubed, 1 minus u squared du. So you're integrating u cubed minus u to the 5th. So it's u to the 4th over 4. So we still have the same sine to the 4th x over 4. But we also have a sine to the 6th x over 6. Okay, second integral on here. All right, let's see how you can do this one. We got a fraction with x minus 3 on top. We have an x plus 2, and I think that might be squared. No, x plus 1 squared times an x plus 2. Interrupt you for your thinking process. Try it. Go. That's B. You're welcome to join us. What's the level of difficulty first one there. Low, medium, high, partial fractions. With the little twist that you have a repeated linear factor.
Mhm.
You have three fractions, something over x plus 1, something over x plus 1 squared, something over x plus 2. And your job is to find the somethings, and all three somethings are just constants. How far did you get? Did you get your constants? 5 is A. Is -4. We'll see again. -5. So you guys can get those. Now ask me.
When do you know, for like, when do you have the not super class?
Yeah.
Yeah.
Because I thought you did one.
A prime quadratic factor. So this isn't considered a quadratic factor. This is,
So it's inside.
and it's inside. And a plus. If it's a minus and it's not prime, then you factor it.
So if it was like x squared plus 3, then you'd have it in the fraction ax plus b over. Okay.
That's right.
And if that's repeated, would you have like ax plus b over x squared plus 3 plus b cx plus b over x squared plus 2 squared?
Perfect.
Okay.
All right, so when I'm cross multiplying, A is going to cancel one of the x squared plus 1s from there, but leaving me 1. The b is going to cancel both of them, so I just have a b times x plus 2. And the cx plus 2's cancel, so I'm going to have the c times x plus 1 squared. Then what? Okay, get the cheap ones. Now that's -1. So over here I have a -4. If x is -1, that's 0. That's 0, and we have b. -1 plus 2 is 1, so b is -4. To get the other one, we take x to be -2. So that one's gone, that one's gone. -2 plus 1 is -1 squared is 1. So I can see over there, -2 minus 3 is a -5. And then you grab any number you like, 0. So on the left-hand side, we have -3. A is going to be multiplied by 2. B is going to be multiplied by 2. C is going to be multiplied by 1. D is -4. So -4 times 2 is -8. C is -5. So -8 minus 5 is -13. Add that to the other side. And I got 10 over here is 2a. So A is 5. So we're putting. Did you forget the 2-hour day too?
Yeah.
Golly. All right, so we're integrating A, which is 5 over x plus 1. B is a -4 over x plus 1 squared. C is -5 over x plus 2. Is that part okay? And they're not all logarithms. This one we're integrating 1 over u squared.
Yeah.
So you're integrating u to the -2. What's the integral of u to the -2 du?
Negative u to the -1.
-u to the -1. So we get 5 times the natural log of x plus 1. Negative gives me plus 4. U to the -1. I can put it down here as x plus 1. And then -5 natural log of x plus 2. Okay? You can see that. Just remember that the interval 1 over x squared is 1 over u squared. Okay, what do you know about the interval I labeled as C?
So you can take out a half, 1 over 2, and then multiply by 2.
Multiply the x through.
And then
Let's do different integration by parts integrals.
yeah. So that is 1/2 times x equals x. Or else,
All right, so what was the formula for integration by parts?
UV minus VD.
There you go. So in the first bit, here's the 1/2 them all together. UV is x e to the x minus the integral of v times du, so we're integrating e to the x. What's the difference when you use an e to the negative x?
X e to the
Got that, right? And so if I do my uv minus the integral of v du for that one, I have uv, so I have a minus x e to the minus x minus the integral of v du, but that minus comes here, and e to the negative x dx. So we'll have, no problem. Let's see, let's move that camera over. Okay, so we got the 1/2 way out front. X e to the x. And then we're integrating that e to the x. Integral of e to the x is?
E to the X.
And we got the same deal back here, but I have a minus x e to the negative x. When you integrate e to the negative x, that makes that a minus e to the negative x. Okay. So this was the thing in that section we skipped. This thing in the parentheses is called the hyperbolic cosine. So we don't need to learn the derivative formulas and antiderivatives for hyperbolic trig functions because they're written as linear combinations of e to the x and e to the negative x. All right, let me see what integral b is. Integral d, oh gosh, I almost know the answer by looking at it. 1 over the square root of 4 minus x squared is what's in the integral sign.
arc sine.
Almost. Oh, is it? Oh, it is an arc sign, isn't it? Oh, golly. Yeah, you're done.
Sin 50.
Let's do a permutation of this then. That one and this one. This one's just spit out the answer, right?
Yeah.
It's the arc sine of x over 2 and you're done? Come on. You did that on a test, you have to be paranoid, right? There
Yeah.
has to be something more to the test than writing out the answer.
That would-
And now the integral.
That would mess with my head.
That would mess with my
Oh,
head
yes.
too. Do the other two. The other two are trig sums.
Don't trust me.
Now, you'd be thinking, I didn't get enough sleep if that's that easy. So try it with the x squared is in front of the minus sign, and then try it if there's a plus sign between them. Those are not quite the arc signs. Maybe we should even add a third one to this. There, that gives you each of the types of trig substitutions in those three intervals. So your process of thinking is you know this and you know what you're supposed to do. That's what's driving you to do the substitutions for each one, which one they most look like.
So here,
Which one do you consider the first one, the x squared minus 4? What did you take for x? Secant, two secants,
Two sheets.
right? Is the secant is in front of the minus sign? This one, x is 2 times the secant of theta, but don't forget the dx. What was the derivative? Okay. Everybody remember that one? Did you guys all start the same way? So let's see what we get when we substitute that in. I'm going to have 4 secant squared theta minus 4 under the radical sign. As part of my dx, I'm going to have a 2 secant theta, tan theta on top. Okay. So what happens with the 4 secant squared theta minus 4? And then when you take the square root of that, you have the square root of 4 tangent squared theta down here, so it just becomes 2 tan theta. Okay, the tan theta is canceled, the 2's cancel. So all we're left to do is integrate a secant of theta. That's one to memorize. Just a natural log, no negatives. And we're going to get it back in terms of x, right? So from here, x over 2 is the secant of theta. X over 2. Let's see. Draw a triangle. Put a theta. Secant is hypotenuse over adjacent. So this side has to be the x squared minus 4 into the square root sign. And tangent is opposite over adjacent. You're right, that's the first one. Okay, let's do the one right underneath it is the second one.
So that one has to be like, two tangents. And that would be two,
Okay,
the integral would be the integral of 2 squared over 2 plus 4.
yeah,
And then that squared changes to 4 c squared.
as tan squared plus 1 is secant squared. So if I pull out the 4, I'm going to have a 4 secant squared under here. Now it's under the radical sign, so I can take the square root of it and get a 2 secant theta on the bottom.
And then that's the distance of the
So again, we're integrating a secant of theta. Again, we get a natural log of secant of theta plus the tangent of theta. And this time, x over 2 is the tangent of theta. So the x is over here, and the 2's here, which makes the hypotenuse 4 plus x squared. And so the secant is that square root divided by 2. And the tangent we said was x over 2. Okay, so the third one has 4 minus x squared, like it did in the inverse sine problem. We'll put an x squared in the numerator. So the third one has an x squared here, 4 minus x squared here.
Do you just treat this like the same one? It's at x, the same thing?
The x squared is behind the minus sign.
Right.
Each of these has the trig function behind the minus sign. So this time you take an x to be 2 sine theta. See what it simplifies to.
skipping steps and a lot of steps applies to 4 sine squared.
4 sine squared of theta,
dt.
okay? And you know how to integrate sine squared, right?
So it would be 4 times theta over 2 minus sine 2 theta over 4 plus c.
Okay,
But we have to change theta to arc sine let's see, arc sine of 2.
okay. And if you want, you can replace the sine of 2 theta with 2 sine theta cosine theta. X squared on top becomes 4 sine squared of theta. Joining that is the dx term, which is 2 cosine theta d theta. And then we have 4 minus 4 sine squared theta under the radical sign. After we factor out the 4, you'll have a 1 minus sine squared. And that was our cosine squared. So the radical sign is holding a 4 cosine squared of theta. We can take the square root of each term and get a 2 cosine theta in the denominator. Those cancel, you're integrating 4 times the sine squared. Sine squared was theta over 2 minus sine of 2 theta over 4. But instead of sine of 2 theta, we can do 2 sine theta cosine theta. And that way we can draw our triangle and get values. X over 2 is the sine of theta. So x over 2, so that the adjacent side is the 4 minus x squared. And so theta itself is the inverse sine. Sine of x over 2, cancel here. Sine of theta was x over 2. Cosine of theta is the square root of 4 minus x squared over 2. And then you have the 2 after you cancel. And all those 2's can disappear if you send the 4 through there. Some version of that. So I'm going to give you some stupid little arc sine integral. Change it to one of these 3. Again, you don't want a Cal 1 integral and Cal 2 test.
People.
The end of the integration. Yep, those were your 4 integrals. And what were they? There was a UDU integral of trig, partial fractions, integration by parts, and then what should have been a trig sum. Okay. Now you're going to integrate from 2 to infinity, 1 over x cubed dx. Integrate from 2 to infinity, 1 over x cubed dx, with all the proper steps.
Like, all of the brilliant, stuff, but not really. Can you do that?
And employ bad calculus?
Yes.
You want to do bad calculus on the final after spending a whole semester trying to learn how to do good calculus.
But I know the good calculus.
But you just don't want to show it. I know it. I just don't want to show it.
Exactly.
Why should I show that I've learned anything when I can just get the answer?
Exactly.
God, you guys are just engineers. You make me cute.
And when you know that, that is the answer.
You know what? In your real life engineering, you have a problem that has no definitive answer. So it's the steps that get you there that are more important. You're literally inventing the answer by taking the proper steps. I remember my son's first week on the job, he called me and said, Mom, they're asking me to do something that the laws of physics don't allow. And that doesn't mean that he couldn't do it. It means the laws of physics didn't allow it. They had to figure out a way around that. And that was like 5 months ago, and now they're knee deep into other things. You just start doing it until you find something that works. So the answer is not important. I know the answer. The answer is it converges. So what?
Yeah.
So let's all pretend that you're 40 years old and your 20-year-old child came and said, Mom, Dad, please show me how to do this integral. You don't just say, oh, that converges. You say, here, look. The first thing you do is you replace the infinity symbol with a letter and make a definite integral out of it.
If you don't understand that, you yell and louder.
Just say it louder. That's right. Just say it louder. All right, now it's a definite integral, so now you can integrate with the power rule. Add 1 to the power, divide by the new power. So you got x to the -2 divided by -2. X to the -2 divided by -2 gives me a -1 over 2x squared from 2 to n. And then we put the n in, and then we put the 2 in, and we subtract. And then what do you say? You say that the n goes to infinity, so that goes to 0. And so 1/8 is the value of this integral, so it converges to 1/8. And none of those steps were painful. But here's the point. This is the last time that we'll spend together, not together, Zoom together, ever. And don't you want to spend the entire 2.5 hours with me on Tuesday, Monday, Tuesday?
No.
Not even like
A barrette would be, a barrette would be. Okay, fine. So you're telling me I want to just do a half-assed job on my final. Get the heck out of here.
Yeah, it gets me there.
Okay. Okay, let me get those letters of recommendation back and edit them.
I get some of that scholarship.
All right, what do you think about series? You want to look at series? Okay, I'll put all these down here. Let me see how I'm going to write these. The first one, you know the answer. Converge or diverge. Sum from k is equal to 2 to infinity. 1 over k minus 1 over k plus 1. Let me converge or, okay, minus 1, sorry. Converge or diverge, and what is it that you're using that tells you such? This is number 5a. Number 5b. We've got k is 1, no, k is 3 to infinity. 2 plus the natural log of k over k. Do those two first.
So A would be convergence -1 because by culture.
Okay, this is telescoping. Because, so we're going to show that it's telescoping. When k is 2, you have a half minus 1, because 2 minus 1 is 1. When k is 3, you have a third minus a half. When k is 4, you got a fourth minus a third. And so when k is n, you have 1 over n minus 1 over n minus 1. And so that shows you that's gone, that's gone, that's going to be gone. What's going to be left out here at the end?
-1 plus 1 over d.
-1 plus,
Or
which
one
one's
over-
going? This one went with the last one, so there's something going to knock out the last one. So you're going to have a 1 over n is your Sn. And so as n goes to infinity of Sn, you're left with -1. And then the punchline is the sequence of partial sums converge.
So if we see positive and rise between the partial sum.
Yep.
The positive and
I'll let you have it either way,
okay.
but that's the expert way to write it.
Well, look at that.
I'm going to show you how to expertly complete your final exam, and if you want to do your little half-A work on it, you do that.
So does that mean we can get partial credit?
Well, I'll give you full credit for doing half-A work. Why stop now, right? And you guys can learn all kinds of junk.
Yeah. So, very long students.
All right, what do you know about part B?
Use it.
You can, yeah, you can use it in a test.
Just split it.
You can split it into 2.
Yeah.
Right, so you have divergent plus divergent is divergent.
Yeah.
Right? How come you couldn't do that here? Isn't that divergent and that's divergent?
Because it's weird.
No, because of that. Because of the minus. The only is true for plus. Okay? Divergent plus convergent is divergent. Divergent plus divergent is divergent. Convergent plus convergent is convergent, but not minus. For the same reason that infinity minus infinity is not 0. It's indeterminate. Okay? So 2 over k is a p series. P is 1. Log of k over k is a q log series where q is 1. Both are smaller than 1, so they both diverge. But you can do an integral test. All right. What's next here? K factorial divided by e to the k.
Ratio.
Quicker than that.
Just for that.
That's for
Oh, yeah.
divergence. In factorial above the number to a power, your tower of power. The numerator grows faster than the denominator. So we say the limit of k factorial divided by e to the k is not 0. So by the test for divergence, see this divergence. If it were upside down, then the limit's 0, and you do the ratio test, right? E to the k divided by k factorial does have a limit of 0. That doesn't tell you it converges. That tells you to do a test. And then you do the ratio test.
Quick question.
Yes,
Is test for divergence not equal to 0 or greater than 0?
not equal to 0, right? in a series, a necessary condition for convergence is that the kth term goes to 0. Not a sufficient, just a necessary. Okay, part D. Part D. We get onto this, we've seen on this Jimmy thingy. So I can fit part D right here. I got a sum from k is 2 to infinity. Inside parentheses, I have a fraction. Outside parentheses, I have a k. 4k minus 1 is inside the parentheses. Divided by 3k to the 5th minus 6.
Retest converges.
Retest convergence. The limit as k goes to infinity of the kth root of the entire kth term. And that's taking the limit of just the stuff inside. What's that limit?
0.
Here's where you compare things in size to 1. You compare things in size to 1 for the ratio and the root test. You compare things to 0, I guess, in the limit comparison test. Right? Okay. So smaller than 1 means it's convergent. All right, all right. Can't see the next one. I need glasses. Does the given sequence converge absolutely, converge conditionally, or diverge? Explain completely. So as I write this down, I want you to tell me what it means to be absolutely convergent. And what does it mean to be conditionally convergent?
It's absolutely convergent. Converges with absolute value.
Converges with absolute value or with the general ratio test. It doesn't converge with absolute value, but converges with the alternating series test. Then it converges conditionally. And we're looking at the series, -1 to the k factorial, or 2 to the k. Does it converge absolutely? Does it converge conditionally? Or does it diverge? More detail. K goes from 1 to infinity. It says 0, it has to start at 1, since there's a k squared in the bottom. It looks like with a 2 to the k is a k squared, even worse. All right, make the 2 to the k a k squared. But either way, you're done, right? Because that's no different, or not much different than the series k factorial over e to the k.
So are you allowed to use divergence test
Yeah,
even when it's alternating?
yep, because in the alternating series test, you need this term to go to 0 as well. So no, because the limit k factorial over k squared is not 0. Conditionally convergent, no, because limit k factorial over k squared is not 0. Yes, it does. There you go.
So moral of the story, use test for divergence.
Always do the test for divergence. Necessary condition for a series to converge, whether it's alternating or not, is that the kth term goes to 0. All right, the first 3 terms of the Maclaurin series for f of x is the square root of x plus 2. I forgot what I told you, square root of x plus 2. Maclaurin series means the center is where? 0. So you don't have any x minus c's, you just have a bunch of x's out there. There's 3 terms, so that's f of 0 plus f prime at 0 times x over 1 factorial plus f double prime at 0 times x squared over 2 factorial. For right, those are your first derivative and second derivative. And we evaluate those at 0. F of 0 is the square root of 2. F prime at 0, we got 1 over 2 square root of 2, since it'll be 2 to the negative 1/2. F double prime at 0 is minus 1 over 4 times the square root of 2 cubed.
Last question. We simplify the second derivative to
Where there's 2 square root of 2? About that? As the square root of 2 squared is going to be another 2, 2 times 4 is 8. That's fine. That looks prettier, doesn't it? Sure. Go further when it's just algebra. Don't go further when it's calculus. Yeah, show off your algebra. I'll be really impressed by that. And so this says that the square root of x plus 2 is equal to the square root of 2 plus 1 over 2 square root of 2 times x minus 1 over 8 square root of 2 times x squared over 2 factorial. Good there? All right, now the obligatory vector problem. I'm going to give you 2 vectors. Vector u has components -1, 2, 0. Vector v has components -2, 4, 2. Questions on this test say, find a unit vector in the same direction as the vector 3u minus v. That's part A. Part B asks, are u and v perpendicular, why or why not? And add a part C just for fun, u cross v. Give me a u cross v as well. Find a unit vector in the same direction as 3u minus v, u and v perpendicular, explain, and find the vector u cross v. We'll take the wall out. Oh, wow. Okay, so where does the person like me who likes to use chalk get to go? They're running me out of the building. With all these fancy classrooms, and then you guys want to take online classes. So a vector in the same direction as another vector is just a scalar multiple. A unit vector in the same direction takes that vector and divides it by its magnitude. So we first find 3u minus v. So 3u is negative 3, 6, 0. Then I got to subtract from it. 3u minus v is negative 3 minus a negative 2 gives me negative 1. 6 minus 4 gives me 2 here. 0 minus 2 gives me a negative 2 there. And so then the unit vector, take that vector and divide by its magnitude. 1 squared plus 2 squared plus 2 squared. So that's 8, 9. Let's divide by 3. Okay, so take a vector and divide by its magnitude to get a unit vector that has the same direction. I change the signs and it has opposite direction. How can you tell quickly if two vectors are perpendicular?
Dot them.
Got them. Is u dot v equal to 0? That is what the question is. So u dot v, u I get -1 times -2 is 2. 2 times 4 is 8. 0 times 2 is 0. That's not 0, so they're not. All right, now you're crossing them for me. You get that already?
4, 2, 0.
4, 3, 0.
All right, so let me just do my little shortcut. That way gives me 2i.
So hold on, that just didn't say shortcut. You need to have higher level calculus.
Am I getting this class for a grade?
What?
Would you like to see my Cal 2 grade?
Yes.
We made all A's. Get out of here. I made a D minus. Oh, is that okay? All right. I had all A's in college, except I took a business law class because I had a boyfriend who was a business major, and I thought, well, that'll be fun. God, was that not fun? Made a B in business law. B for business. Please get degrees in business. All right, that's 0J. And that's a -4K. All right, and that's minus a -2J, so that's +2J. That's a 0I minus the -4K, so that's a 4K. So I got 2, 2, 0. Is that what you got?
No.
You got 4? Oh, because 2 times 2 is indeed 4.
1.
4, 2, 0. Well, 2 times 2 gets me every time as well.
That and 1 plus 1.
1 plus 1, which base are you in? So that was fall of 19. And we putzed around and it got it done in less than 2 hours, right?
True.
And I added parts, I added like 3 or 4 different problems to each problem. So if you prepare, if you spend a week not doing calculus, Tuesday you're gonna feel pretty slow. You do some a little bit each day, blow up your other tasks, those are not important.
Correct.
You know, because one day somebody's gonna ask you, what'd you get in calculus, and I want you to come back, I made it.
Honors.
Honors. I didn't have honors in college. Gosh. What else do you need to know for your final? Math? The answers. The answers.
So what is the format of submitting it since we're doing the overshoot? Is it still on Blackboard?
It's gonna open on Blackboard. Our test begins at 4:30. Is that right? So I'm gonna scare you and open it at 4:45. I'll let you sit there and panic for 15 minutes. Oh my God, she said it was gonna be here. And I'm gonna watch the emails come in. And I'll say, what? You didn't get it? I put it on there. No, the test was at 10 o'clock this morning. Where were you?
I sent out an email.
So I'll have the test open in about, 10 minutes before that in case you wanted to print it. And then you do all your work in a neat and organized manner. And then hopefully send me a PDF of your work.
Oh, email it like usual.
And then I'll pretend to grade it.
Yay.
I'll fax it to you.
You'll fax it to me. I'll get my fax machine out of the attic. Good? Marvelous semester, you guys. You're on your own for the rest of your mathematical career, but my office is upstairs. Anytime you need me to ask a math question, come on by and pretend you came by to talk, and then we'll do math.
I'll remember you, Cal 3.
I can do some Cal 3.
All right. See you next
I can do some Cal 3. I can do some of that engineering statistics and differential equations, wherever you are. Linear algebra.
What's that?
Thank you, guys. Marvelous stuff. Thank you very much.
Thank you.
Take care. Thanks. Bye-bye.
Have a nice one.
Thanks.
Thank you for the recognition. No, I know, but seriously, thank you.
You're more than welcome. More than welcome. Found it on the chair, I don't know what it is.
What other classes do you
I don't know what that is. For the last few semesters, I've been teaching.
I thought you meant taught house three.
I have taught Cal 3 a long time ago, years ago, maybe 2017.
So it's been a while.
Yeah, but people would like to teach Cal 3 honors. And that's hard to get. Nobody likes to teach Cal 1 honors. They give me that.
Why not? More.
Or, yeah, you've got PhD in that, you can teach Cal 1, that's a big one.
Well, thank you.
Thank you.
Sound device right there.
Bye, thank y'all.
You'll see, I'll come by.
Good,
Don't
good.
worry.
I'm glad.
Many